when you get into the details of quantum, when I give like lectures and stuff on this, I say to people, if you think you understand this, you haven't understood it. None of you should be sitting there going, oh yeah, it makes complete sense.
And is quantum a thing whereby like people have figured out what it does, but there's no logic to why it works? Or are they actually figuring out the logic?
No, people don't. You get to the depths of quantum, and at one point you're into what makes up our universe. People don't know how quantum works. They just know that it does work. It's been proven with tons of experiments.
Is this because we're just in a simulation and it's part of the supercomputer running us?
Yeah, I will say we've had a few sort of moments in the office with a few beers where one person starts up and like, what's really happening? And we go down that road of like philosophy and working out what the universe is made up of and stuff. By the way, we try and sort of not do that when we're trying to build a quantum computer, because you just get way too distracted by all the interesting stuff.
I think it's amazing. I would do work experience there if I could. This sounds fascinating. Did you find any weird? Oh, I'll dig it out later.
He just didn't like how random it was, and the fact that you don't know. So quantum all relies on probabilities, and I could try and give you
Should we do a 101 on the physics as much as you can do?
Yeah, I can have a go.
Yeah, explain it like we're 3.5.
As long as you promise to interrupt me and tell me I'm not making sense.
I've built a career off it.
So maybe the core thing about quantum is that one thing that you don't think should be able to do two things at once can do two things at once. I probably lost you already.
No.
I always describe it as light switches, right? So people in electronics, they all know about binary circuits. Things are on or off, like light switches. We all know a light switch can be on and off, on or off. That's like the normal world we live. Like things are binary, 1 or 0. In quantum, the weird thing about everything quantum is you engineer these systems that can be 1 and 0 at the same time. And this is the bit where I said, I'm giving a lecture on this and people go and like nod their head like, yeah, I understand. You really shouldn't understand that something can be 1 and 0. So I always sort of describe it. If you're imagining a light switch and you're like flicking the light switch backwards and forwards, or you're trying to hold the light switch in between, you're not really allowed to do that. It should be as weird as sort of imagining like me to say, okay, there's a room and there's 2 exits to that room. You as a person pick one exit or another exit. That makes sense to us. That's binary. That's the world we live. In quantum, if you were a quantum thing, you'd be able to leave through both exits
at the same time.
I've seen
that because that's the light slit experiment.
Yeah, exactly. So that's the basis of all things quantum. So the fact that these things that we use single photons, so single particles of light, and we do the Young's double split. We do the light thing where things. So basically,
do you know about this, Danny?
Yeah, I remember reading about it. I mean, I don't understand it, but I know what you mean.
Well, the main point is you really shouldn't. None of us understand this. Like none of us sort of take a look at this and go, oh yeah, it makes complete sense. Light goes through in 2 different directions at the same time. Like all of us sort of physicists working on this stuff, we all know that the light has to go one way or the other. It has to go out one door or the other door. Can't whenever anyone tries to think about going out of both doors, because these things are not divisible. So what we're doing is sort of the reason Einstein didn't like it. It doesn't make sense. So we take these single photons.
What is a photon?
So it's a single unit of light. So if you imagine light bulbs, sort of lasers, everything like that, what we think of when we think of light, is all made up of trillions and trillions of photons. So single particles sort of flying at us. And this is now in the other sort of weird quantum world of maybe people have been taught, in their upbringing about light being a wave. The other way of looking at it is a particle. So just imagine every light bulb's emitting loads of these fundamental particles, these things called photons. So what we do in our company is just isolate just one of those single particles. And you promised to sort of interrupt me if this is starting to be not useful. So we isolate just one of those particles, and this thing cannot be divided. It can't go in 2 directions at once. It has to pick, classically.
So when photons are hitting us,
yep,
it's trillions of individual ones. Okay.
Absolutely.
And how do you extract a single photon? And how do you take hold of that?
Weirdly, I get asked this question all the time.
Yeah.
I mean, this is pretty much what our business is made up. We spend most of our time just doing this. You basically take a really well-controlled light bulb. You know exactly how many photons it's produced, and you just do a ton of filtering. I guess that's the probably easiest way to describe it.
Until you just get one.
Until you're just left with one.
How do you know that one has shot out? Do you see it?
Well, no, because we'll get into the middle of weird quantum stuff. You're not allowed to look at the photon, because if you look at it, it destroys all of the quantum effects. So what I was going to get on to is when you send a single photon at a mirror.
Yeah.
So imagine this mirror can reflect half of the photons, and it lets through half of the photons. The photon doesn't do one or the other. Remember, I keep going on about this. It can't be divided, this photon. It has to pick one or the other, or at least so we thought. But instead, the light, the single photon, becomes a quantum thing where it does both. So it both gets reflected and it goes straight through the mirror at the same time. So this is this thing. Now it's a quantum thing. So this is now, basically our computer's built of loads of those operations where one photon gets split millions of different ways into this big sort of maze-like thing. But it's still one photon, but one photon has been basically split up to cover all paths in your maze, if that makes sense.
So has the photon, has it replicated itself?
No. I mean, this is what I mean. If you really understand this stuff, I will say, any of your audience, you should not be sitting there going, yeah, it makes complete sense.
Okay.
This photon is still one photon. It's not been replicated. It's one photon. But because it's quantum mechanical, it can take loads of paths at the same time.
How do you know it's taking those paths?
There's that's a bit more subtle. This is back to the Einstein, sort of him coming up with an experiment to prove it. Basically, there are different outcomes because if the photon is taking loads of different paths rather than just one path, it can do really weird things. It can interfere with itself. So two possible paths of the photon might sort of at a later time, imagine this big maze, the photon's passing through this big maze. Sometimes two different paths of the maze will come together. Then like another part they'll interfere with each other and produce an effect that you don't get if the photon's just going through the maze like one at a time. So yeah, anyway.
How was quantum mechanics even? How did people figure it out? Or like what happened that made somebody go, you know what, there's some weird shit going on here?
There were so back at the turn of the century, so around 1900s, there were just a lot of experiments that people didn't really make sense. People tried to sort of a bit like the double slit experiment. So there's an experiment that you can do which makes sense when you've got lots of light. So people try to pass light through these two slits at the same time, and you get this sort of weird pattern. And then people slowly dialed down the light power until they just had one photon. And at this point, they were like, okay, the light will choose it will choose to go through one door or the other one. And they still observed the same effect as when they had lots of photons going through two doors.
Okay.
I probably lost you. But anyway, there were loads of experiments that didn't make sense. And around like 1900s, sort of Einstein and all those types of people suddenly sort of went, oh, hang on a minute. Like what we think we know doesn't work. We need this. And this whole new theory emerged sort of to try and explain what they were observing, what they were looking at. So, and that's sort of what people, in the field, people describe this as like quantum 1.0. And all of those effects get built into how people design semiconductor chips. So you can't design a like modern day computer, a semiconductor, without understanding quantum. But what?
Hold on, because
it sort of describes how all electrons pass through materials. It describes all semiconductors. You can't really describe like a transistor, like the sort of fundamental thing in a computer, without understanding quantum. But what I was going to get onto, so now sort of turning to quantum computing. So all of that stuff has existed for like 100 years. People have known that this really weird physics is there. But slowly over the last 100 years, people have been able to get better and better at actually making these quantum effects. So actually creating these pieces of light that are in two places at once. And so, that's the start of a quantum computer. So if we take an electron or a photon that's in two places at once, that's a single qubit. That's a single qubit quantum computer that you can start using. And now we're at the stage of having, in our company, we've got a 10 qubit machine. So we've got 10 single photons, and all of those are in two places at once or more places at once. And IBM have got 100 qubit machines. So all of a sudden they've got 100 sort of, in their case, sort of electrons all exhibiting quantum effects.
Yeah, I'm going with you at the moment.
Good. And why does observing that break the quantum effect of it?
I don't know if there's a good way to describe that. Sorry.
So
other than just all this stuff, just it can't be observed. Like weirdly,
You mean if when you say it can't be observed, in that if you were looking at it, your eyes are what destroys it.
yeah. So if you were looking at
But
this,
if you had your back turned, it would be fine.
yeah.
That's fucking weird, man. I feel like I need a joint, and I don't even smoke weed.
Yeah, that's why a lot of physicists look a bit spaced out when they talk about this.
Hold on. But it's only if a human looks at it,
Oh well,
or a camera.
do you know? No one really knows. I mean, this is now at the limits of like philosophy. Like, this is what I mean about no one really understanding. Like, what is this?
Yeah, but hold on. If no one's looking at it, it works because your computing works. Your quantum computing works.
Yeah,
But if you were looking at the photon in your quantum computer, your quantum computer wouldn't work.
correct. Yeah,
But if a camera looked at it and not a human,
yep. It's as good as I mean, it's as good as it still destroys the experiment.
so anything, so even a dog, if a dog was looking at it, it would destroy it. Okay.
I don't know. I don't know. We don't allow animals in our lab.
I mean, that's to me, that's an obvious test.
That's why you're not.
Jesus
Do you know what?
Christ.
Someone must have done that experiment.
Yeah.
I can't.
But even now, I'm like, hold on, what do you mean? If I look at it, it destroys it.
Do you know? I mean,
Is it because the photon wants to come to me?
I don't. I'll be honest and just saying this is like a whole massive area of sort of philosophy that I
But hold on, I can't put philosophy and computing together because computing to me is maths. It either does its thing or doesn't. Philosophy is like, it's like figuring this shit out.
Well, so what I mean is that when we're building our quantum computers, we deliberately just don't think about all this stuff. We just know all this stuff works. There are loads of rules that tell you how it works.
We don't know why.
No, you don't. Wait. I mean, the same. Actually, I'm trying to think. I mean, I guess there are loads of comparisons in companies where you don't really know what's going on, but you don't care because you're just trying to build a product.
It's my whole life, really.
But that's the same as what we're trying to do. We're trying to just we harness. We take advantage of this 100 years of research of like how this stuff works, why, without worrying so much about why it works, and that's good because we can still build computers from all this stuff. There's loads of weird stuff that happens,